Hi guys, my name is Luke Quinn, and I'll be presenting the the algorithm behind my FM Demodulator that I wrote in CUDA for our CUDA class at Johns Hopkins. So, just gonna give a high level. So basically, I have this hardware component called an RTL-SDR, and it receives these things called IQ signals. Um, they're radio samples, so they sample a signal in time, and they have some value for it. And basically my project is to ingest them and decode them so I get like commercial radio out of it. So I implemented this algorithm in CUDA. The source code's online. You can find it. Um, and on the left, you'll see sort of like an algorithm flowchart sort of thing that covers over basically what I was doing um, for the project. And then I have some lessons learned and future plans slides later on. So this is what an RTL SDR looks like. Uh, it's an idealized RF front end to just receive these IQ symbols. Um, it samples at 2.4 megahertz, and so I get an I and a Q value. I get 2.4 million of them every second, which is a lot, which is why I think CUDA really applies to this use case. It's because we're dealing with a lot of data, and we need to act on it fast because a second of FM is only like a couple words. I've already gone through about a minute of words, so that's millions and millions and millions of samples. So CUDA is great for processing large data sets. This is certainly one of those. So it just looks like that. It has some trivia on it. But let's talk about IQ symbols. This is like the meat of our stuff. I'm going to talk a lot about DSP algorithms because I had to build a DSP algorithm and basically a pipeline for decoding an FM radio station signal. So IQ values, they're just complex numbers. You imagine that we have like an SMA connector on that that RTL SDR. An RF signal is a radio frequency signal. It comes in, and the RTL SDR, which stands for it's like real-time link software-defined radio dongle, is what normally they call it. They just multiply it by two numbers to get a I and Q value, and this is all done in hardware, where the I is an in-phase signal and the Q is 90 degrees out of phase. Effectively, if we look at the bottom left, this like doubles our sample rate, so we're sampling one signal twice as fast because we have two samples on it that are out of phase, and they make like a perfect complex number because the I is just the cosine of the given signal. In this case, I call it M of t, and the Q is that. And when you see M of z, so whenever you see like z in this presentation, that function is a complex function where the t in time is just a real number, a real valued function. And so each I and Q component is real valued, and they become a complex frequency signal when you multiply the Q component by a complex number. So they're like always, you can imagine that is what 90 degrees out of phase means. They have alternate representations. So while, yeah, so we're doing FM modulation. So this M of Z, this complex signal that we now have, it has an amplitude of T. In this case, amplitude is constant. It's FM. FM is not changing the amplitude. And we multiply it by e to the 2 pi I times f, which is the frequency that defines this signal. And as you see, I have an example of FM modulation in like the IQ space over time. And it looks like a giant spring. It compresses as the waves get faster and expands as they get slower. You can imagine that's as you speak at like a higher pitch or lower pitch, or I really should say frequency. But this is what it will look like in a complex space. And actually, if you look really closely, it's going from clockwise to counterclockwise because frequency oscillates. It goes back and forth. It goes back and forth when we talk. So it's from super high frequency to not super high, but like relatively high to relatively like it oscillates. And that's what this spring is representing here. It's the oscillation and change in frequency that our signal is going to experience over time. So let's actually dig into how do we take this sort of like IQ values plotted over time and get intelligible speech out of it. Very first step is let's plot it. So we have a bunch of IQ signals, and we can plot it and make it visual in the frequency domain by actually doing a fast Fourier transform, and you can generate these views. Now these are paraspectral displays, so the higher up it is, the more power this frequency has over these 2.4 megahertz. This is the bandwidth of our RTL-SDR, and all of these peaks are FM stations because we sampled at 100.112 megahertz. That's this little thing here, this little extra singular spike. Everything else sort of has these this is a DC offset. It's an issue that RTL SDRs normally have. But everything that's not a big spike like that is not a DC offset. It's an actual radio station. So the first thing we want to do is shift our signal down to baseband, which is, in this case, this is really actually the center of this diagram would be like 0 hertz, but I'm showing the spectral view as like we sort of do our processing so that the non-digital signal processing expert can understand what we're talking about. So to do that, because we want this station, this is 100.3, we want that station. To do that, we multiply by the cosine of the difference. The difference of these two functions defines a frequency. We multiply by that frequency. Both are complex numbers, they have the same amplitude, so effectively we're shifting in the frequency domain when we multiply in the time domain, which is what I'm showing here. And I show the math. Alternatively, in CUDA, you have I and Q and IS, QS. This is like the I and Q values for a shifting like frequency sampled at a given rate. In this case, we sampled at 0.178 megahertz, and that effectively shifts us to the left if we want to do that. We just throw in a negative. And the math works out there. But the next part of our algorithm is we really need to filter. So previously, you see all these bands. I have 1, 2, 3, 4, 5. There's like 6 or 7 FM stations in here. It's hard to just look at the power spectral display. But we want to filter. So we have one station. And how we do this is we use a finite impulse response filter. In CUDA, you're running this algorithm. You're summing over some h constants matrix. So h times a sample in time minus whatever the current constant you have. And what this does, it's basically we're integrating this signal over the actual spectral display. So you get out essentially the center of the graph. This is a baseband filter, and so when we run it, it integrates and you get just the area under the curve, and this applies over each sample. So this is run on each sample. Our filter window is 51 samples long. So every 50, the sample 0 takes 51 values and compresses them down. And you basically run this sliding window over every single sample. And after you do about 51 adds on every sample, you end up with a much filtered signal. You see, there's no noise here. The power spectral display is it's a logarithmic scale. So if you move up 3 dB here in your like y-axis, the signal is like 50% stronger. So this is so at the top here, this is a much stronger signal than like way down here. Like this is like quieter than you can whisper. It's like almost nothing at all. And I use this format for this finite impulse response filter because it's essentially a convolution operation, and they work really well with CUDA. That's easy to implement. So now that we've sort of like filtered out the noise, we actually need to do FM demodulation. So it requires us to downsample, which I'm going to talk a little bit more later. But essentially, after downsampling, it's like zooming. Just think of it. It's zooming into our signal. So we're like expanding up. So like this signal from before, if we zoom in a lot, becomes this signal. And this has to do with the Nyquist frequency theorem. Essentially, we can regenerate any frequency where we sample at twice the actual known frequency rate. So you'll see this window is about 200 kilohertz big. FM signals have a band footprint of 100 kilohertz. So if we sample at twice that rate, we can actually do our FM demodulation on that. And downsampling is how we go from the 2.4 megahertz sample rate to 200 kilohertz sample rate. So we'll talk a little more about that. But we have to actually do the FM demodulation first. So FM demodulation, any signal abstractly can be written as this. This is in like the paper that I wrote to go along with this presentation. A signal has an amplitude, it has a frequency of the carrier signal, it has a frequency of the message signal, and some phase function that could be a phase offset or something. Um, Most of these are constant. There's no phase in an FM modulation, so this term's 0. And the amplitude is always 1. If you remember our spring diagram, our circles weren't growing or shrinking. They were all the same. And so you really only have this 2 pi f of the carrier frequency plus the 2 pi f of the transmitted message. And so to pull these apart, we really need to find the change in frequency, because it's we're transmitting these IQ signals at some known rate, and when we take the derivative of like the change in frequency, we get out our message. Our message frequency is what we want. So the algorithm here, it's a little hard to read. I copy and pasted these from the paper I wrote, but essentially there's two methods we can do. And the naive method is to just take the complex conjugate of a sample and multiply it by the next sample. And this is like taking the difference, and then you take the inverse tangent of that, and that recovers the angle of our frequency. And then after you have that angle, you just differentiate, which basically means subtract it from the last angle. How much did it change? Now, there's a paper I got this from. This method was complicated because it uses the inverse tangent operation. In the future, I want to implement my radio on an FPGA, so I wanted to avoid it. So with some complex DSP operations, I guess, just take the derivative of that function, that inverse tangent function, and you end up with this big mess. It's still really complicated, but you'll notice the bottom is the amplitude of our signal. I mean, it's like the normalized amplitude of our signal, basically. So we can really remove the bottom and simplify out, because that's constant, just multiply by C. So this is what that previous operations network would look like. But we're going to simplify it by cutting the graph in half and saying everything down here, it's about constant, which in fact it is constant because this is FM. So we take this diagram, and essentially it becomes C times this. And this is really easy to implement in CUDA, because CUDA can sample at any point in time. I can get a IQ sample, I can get the last guy and the next guy, one minus the other. You get the difference between the I and Q values, so those are like these derivatives here. And then the actual scaling part is just to make sure that we are within the right domain when we normalize. You can read the math more closely. But this diagram, essentially, you can implement this on an FPGA or CUDA. It's not difficult to do, because it shows you all of the operations and in what order you need to calculate them. Yeah. So moving on. I talked about downsampling earlier. So after we do our FM decode, we have a band plan that looks like this. There's some mono audio between 30 and 15 kilohertz. There's still a lot of messages in here. We want to zoom in on the stereo input. Specifically at 44.1 kilohertz is what a sound card can play. And that's right in the stereo range. So we're going to downsample to get to that. So downsampling means we're just like rejecting every other sample, or every nth sample just gets rejected. And we only keep every nth sample, and all the other samples get rejected. This reduces our problem size from 2.4 megahertz to, let's say you only wanted every 12th signal, or every 12th sample. You do like a poll and you say, all right, I want every 12th sample and ignore everything else. And if you do that, you divide 2.4 megahertz by 12, you get to 200 kilohertz. And then to actually play audio out, we do it again. And we downsample by 4 that time to get to around 44.1. The math looks a little bit off, but that's because we're not exactly at 200 kilohertz. We're a little bit over because we divided by 12 before. So that gets us this audio scaled sample rate. So like this has a real signal inside it that is stereo, so you can actually just play it. These are the voltage oscillations that you can play, because these are actual like IQ samples that we've taken an FFT over. And you'll notice that, well, where the heck is the rest of the graph? radio samples are real. They're not complex numbers. And so when you actually do your FM demodulation, uh, all of the like complex domain is sort of just lost because it doesn't add anything. You don't learn anything. You don't learn anything new by having like the complex values there. So this is actually a real valued. These are now real valued functions. You basically just chop out the Q component, and the I would then be the voltage that you would play to your speaker. Um, so high level, why did I go over all this DSP noise? Is that my project, the core idea behind it is that each one of these operations is a CUDA kernel. And then the overall process, it could be a CUDA kernel, but you can plug and play. Maybe you want to use a different filter or something like that. You have the choice to sort of drop in and remove components or tune components, and this flow, this like pipeline works really well in CUDA for sort of hyper parameter tuning. So let's say I didn't want 10.3. Well, great. You only have to change your frequency block to say, let me add in a different parameter at the frequency shift stage, and then we'd be sampling a new FM station. Or let's say that you wanted to use a more complex filter to get a clearer signal out. You only have to change out the filtering of the noise stage, and then all of these others like sampling methods, they don't have to change. And that's the idea behind my product is every DSP step should be a kernel module, and then the whole process is sort of plug and play. You can swap and go as you like. So I have this fancy chart here, but essentially there are a couple things I didn't get to in this project, and there were a couple points for like specifically for the CUDA stuff that I really wanted to touch on. So all of the CUDA C code that I generated is meant to be really portable, and you can basically stitch it up to a reader thread that could actually read the RTL-SDR like hardware object directly. Because we had Vocarum, that wasn't really possible in the cloud environment. And so I didn't focus on implementing that part. I just made it so that the C code could really be shifted to another thread, and that all of the like actual like complex DSP coprocessor work, it should all be done on the GPU, so the host processor has time to actually handle the device I/O. And if I had a chance to integrate, I would do that, and have like an RTL-SDR reader thread involved, so like you could actually like be passing in work constantly to this CUDA object and not have to be like just running on I currently I just run on a file that has a bunch of IQ signals in it. It's like a 10-second audio file, and it just my code reads the whole file in and then processes it in one batch. Um, but everything about my processing is written so that it would work well with like a stream object. Everything's tied to a CUDA stream, and so that allows you to really parallelize the code effectively. Another thing I would like to add is more filters. I used a Blackman filter because the implementation is easy. Um, but technically, Blackman filters can be tuned so that they listen more closely into certain frequency ranges, or they can filter out more noise, or you can give them a different pattern if like you have some weird noise pattern that you are experiencing. The filter code is made to be modular, so you switch out your constants matrix and then you have a new filter. Um, it's written to be like that. It's just that I only added that one filter to get it work. And finally, I really want to implement this on an FPGA in the future. Uh, Future plans, future projects. It's not quite CUDA, but it's just more processing power, and the problem is very interesting. I also have some sources that I used. If you have any questions, you can contact that email. Um, I've used some of the diagrams here would come from some of these articles here, so I just want to cite these are all the sources I've used, and just respect that. I didn't build this whole thing on my own. There are a lot of people that have done similar things. I think I'm the only person that's done it in C and CUDA that's going to be on the internet. All of these other people, they mostly work in Python, or they have like the generators for like DSP, sort of like those Blackman filters. They write some of them in C. But yeah, so thank you very much. That was my CUDA presentation, and have a nice week.